Hello. Now let's try exercise or problem 10 this 1st of January 2021. Yeah. So we have a fixed lattice, G2 and G3 given, and Weierstrass P function. Let U be a non-constant function on a connected open region which satisfies the differential equation. Prove that U is the translation of the Weierstrass P function. Right. So first, there's no dependence of the z value, explicit dependence in the differential equation. That means that every translation is a solution as well. That's the first point. Now we have to do it the other way around. We are going to have to use the uniqueness of solutions to ordinary differential equations. And so you write it in this form. And when U is distinct from 0, there exists a unique solution let's just take it at a point. So if at some point it's distinct from 0, then there is a neighborhood in some neighborhood. We should just start writing hood, I think. Solution in neighborhood of Z0. Now let's just call that value Z0 or U0, that's better. And we know that the Weierstrass P function is onto this is wrong arguing. It's when the square root here is distinct from 0. So the zeros let's call them E1, E2, and E3. And we know there are 3 distinct. Do we not? Well, let that be an open question for the time being. I don't really think it's a problem here. Now, so it's when it's different from all of these, there is a unique solution in a neighborhood of Z0. And that can, for one of the signs, no. So we just have to see which one it is. Or rather for each. with same sign as U has. So given a solution, one of the signs is chosen, provided the derivative is non-vanishing, right? And we know that the Weierstrass function is onto so when it's so there are two solutions actually, or 2 points where it gives U naught, and so there are 2 points set where it gives U naught, and they have the different sides of this one. Now we are talking, of course, 2 points in the fundamental domain. That's right, it does. It's because the now because what? It's even. That's why the Weierstrass P function is even. So let's assume that that was poor P. Z naught equals U naught. Oh, not Z naught, that was this point. We have to have another one. Z1 equals U naught. Then we define f of z equals, so that when we insert z naught, we get z1. So this is our alpha. Then they agree in the neighborhood, and it can be expanded by analytic extension to the everywhere except the pole at alpha. Yeah. So if the derivative vanishes, well, first of all, we have 3 constant solutions to the differential equation. So if it's not constant, then let's look at the number of points where the derivative may vanish. That's only for distinct values that occurs for these distinct values, and if that is for infinitely many, having a point of what's called a density point, then they should agree. So the points where derivative vanishes are isolated. That's what I mean. So it's possible to choose a point where it's non-zero. That's insane, because that's just the meaning of being non-constant. So if it's non-constant, then we have a value where it's not equal to one of these 3 0 points. And then we have a unique solution in the neighborhood of the set, and then we go along right. So I believe this answers problem 10.